in the American Southwest are the remnants of an ancient sea. Millions of years ago, in the Permian era, the upheaval of the bedrock drained the oceans and left behind these legs. Dr. Russell Vreeland is a microbiologist based at Westchester University. He has been studying the survival strategies of microbes and has come up with some remarkable results. His study site is a repository for nuclear waste located beside one of the legs. The waste site is right in the middle of nearly half a mile of rock salt. Over time, this salt gradually expands, which is why it makes a good storage medium. But if nuclear waste can be locked out, traces of ancient microorganisms could be locked in. The salt crystals within these walls have lain untouched and uncontaminated since the ocean dried out millions of years before.
I want to find some areas with the pipe. There's one here, yeah. With the...
And inside the crystals, Dr. Vreeland thought he might find traces of the microbes that lived in that long-dead ocean.
Very good example, actually, in my opinion, because we have very nice defined bands and striations. We have, and each of those represents a tiny, tiny droplet of the Permian Ocean that was trapped and has been held in that crystal for 200 million years.
To him, these crystals are as valuable as any gemstone. Inside the crystal are minute droplets of the seawater trapped within as the salt crystallized. A tiny hole was drilled so that the drop of water could be released. Perfectly shaped microorganisms named Bacillus permians were found, relics from the past. But the next finding was truly extraordinary. For 4 months, the microbes were fed with a nutrient broth. They began to divide, then multiply vigorously. After slumbering through tens of millions of years, they had come awake.
Bacterium that we found in the crystal was neither alive nor dead. It was in a state of long-term suspended animation. As a spore, it just literally could do nothing but sit and wait. Amazing part about a dormancy like that is that they don't need nutrients, they don't produce waste product, and they have the ability to just sit and wait until conditions are favorable again for survival.
Yet it seems that life did exactly that. It survived.
I find amazing is life is really tenacious. And once it came about, once it evolved, once it was on this planet, it would have taken a huge event to sterilize the planet. You would have had to heat the planet literally all over, and as deep as you possibly could, virtually melt the planet to really destroy the life.
To survive millions of years trapped in salt looks easy compared to the virtual end of the world.
When you have an impact, you have that instant in which all this energy is converted to heat. But that's only part of it. You then have the vapor that expands and heats up the atmosphere as well. So now you are no longer dealing with just the point of impact and the vapor that's created there. You now have material that's expanding. Eventually some of that material is expanding and goes out of the atmosphere of the Earth, then comes back down. During the time when it comes back down, it's generating more radiation. so that you have the heat of the impact, then you have the material, the vapor that heats the atmosphere, then you have ejecta that returns to the surface of the Earth. And as it goes through the atmosphere, it will create enough energy to literally fry, completely combust any living organism that would exist.
The total evaporation event that occurred around 4 billion years ago was catastrophic. Water as well as salt deposited on the ocean floor evaporated. There are microbes that actually like heat, but not heat like this. Dr. Sleep of Stanford University looked long and hard at early life's survival capabilities. He thinks that he's found an answer. There was a part of the Earth where life could sustain itself, and this was deep below the ocean floor. This graph shows the temperature distribution in the subsurface of the Earth. The red area is the heat from the Earth's core. Nothing can survive in this region. Green are regions below boiling point. Blue are regions just below 50 degrees Celsius or 122 Fahrenheit. Life could survive in the blue zone, the Goldilocks zone, as Dr. Sleep calls it. It has been estimated that the temperatures on the surface of the Earth would have reached as high as 2,000 degrees Celsius, over 3,500 Fahrenheit. What the researchers wanted to know was how deep would the heat penetrate and how fast could it travel down into the Earth? Would the heat from above meet the heat from below?
Across the top of the
The heat from above travels slowly and steadily, about 1 meter or 3 feet every year. The simulation showed that there will always be regions where life could survive.
Any organisms that are living deep underground, like 1 to 2 kilometers thick, will be fairly safe. The heat pulse doesn't last long enough for the heat to propagate down to that depth. It's a little like when you cook a turkey. You can't cook a turkey in your oven in 1 minute. If you try to do that, even if you get the outside very hot, the inside will still be cool. We have the temperatures here. At the ridge axis, things are relatively hot. As we get away from the ridge axis, it's relatively cool. An ordinary organism, you want to be here in the blue.
If life were present 3.8 billion years ago, then the life that we have on Earth now would have descended from life that liked higher temperatures, was more able to survive high temperature waters, and was not photosynthetic.
However, early life needed water, and the water on the surface of the planet was gone. Was it possible to sustain any sort of life in the rocks deep below the Earth's surface? Here in South Africa, that question has been answered. Gold brings wealth to a country, but the job of getting that gold is dangerous.